In Chapter 9, we're going to talk about ionic and covalent bonding and how to build the electron configuration. So we're going to start out with the fact that there are three different types of bonding in chemicals. There's the ionic bond, which forms crystals. So this is going to be an ionic molecule. And I change the color here. Okay, and that's formed when it's an electrostatic attraction between the positive ions, which are called cations, and the negative ions, which are called anions. And so this is an example of an ionic bond. This molecule here, which is lithium, is going to give up this electron over to this molecule, which is fluorine. And so this is going to form Li plus, because I gave one electron away, and this is going to form Fi minus. And so the electrostatic attraction then becomes, because this positive here and this negative here are then attracted to each other. A covalent bond is for molecular compounds. So this is usually a metal and a nonmetal, although the technical definition is cation and anion, and that's because of the fact that there are some polyatomic ions that are nonmetals. Okay, a molecular compound, we've only ever studied two, is going to be two nonmetals together. And here's an example of this. And the difference is that these share their electrons, and that's what causes the bond. So it's a bond formed by the sharing of electrons. And like I said, this is a molecular compound. The last one we're not going to talk about a whole lot, but these are metallic bonds, and these are pure metals. They don't have to be, by pure, I don't mean the fact that they have to be all one type of metal, okay? But certainly copper wiring would be an example of that. Aluminum foil would be pure metals, okay? But also things that are alloys, like brass, which has three different metals in it. Steel. Those are metals that have more than one type of metal present. And so what happens there is that you have your cations line up in some arrangement, and the electrons then are floating freely between these, which is why metals are conducting, because of the fact that this is what's referred to as being a sea of electrons. Those electrons are allowed to flow in one direction or the other. So we're going to focus on first the ionic bonding. So an ionic bonding is when the electron jumps from the metal to the nonmetal to make a cation and an anion. And so each ion then typically ends up with a noble gas configuration. So here's an example. Here's sodium that has one valence electron, which we're going to define what a valence electron is in a minute. Chlorine, which has 7, goes to form Na+, that's the cation in red, and the anion in green. Magnesium is in group 2A. This is 1A. This is 2A. So it has one valence electron. This has two valence electrons. This is in 7A, or in 17, and this is in 7A. So each one of these have 7 dots. And so it takes 2 fluorines to accept both of the electrons from the magnesium. So basically the metal is going to give away all of its what they call valence shell, which is basically going to be from the number of the group it's in. And again, I form an anion from fluoride, a cation from magnesium, and another anion from fluoride. Now when I ask you to do this type of problem, I don't necessarily care if you write this. I won't count it wrong if you do, but I don't care that you write down the right hand side, but the problems in the book do. So what you saw there was a representation of the Lewis dot symbol. Okay, so all of these, the sodium, the chlorine, the fluorine, the magnesium, and the fluorine, these all are the Lewis dot symbols, which basically just is a way of showing the valence electrons. So again, the valence shell electron. So the valence shell electron is the outer level of electrons. Okay, and it's simply the group number. So these are the Roman numerals, but this is 1A, this is 2A, this is 3A, this is 4A, this is 5A, this is 6A, this is 7A, and this is 8A. Okay, and it's important that when you draw these such that they are, you don't start pairing them until after you get 4. So you notice 1, 2, 3, 4, none of my electrons are paired, which means that they're just one electron on each side. And so I'm going to have an element, and then the way that I do this is I'm going to have this imaginary box. And the imaginary box is where my electrons go. So again, if I do it here, that's my imaginary box. And so there was 4 electrons around that. On the 5th one, then they start being paired. And then on the 6th one I pair, the 7th one, 3 are paired and 1's unpaired, and on 8 they're all paired. Okay? And so it doesn't matter what row they're on. This is the 2nd row, this is the 3rd row. The columns basically have the same electron configuration. Or Lewis dot symbol, I'm sorry. So it wants me to draw the Lewis dot symbol of silicon. Okay, so silicon is right here on the periodic table. It's in group 14, so remember that if it's a 1 through 18, it's 14 minus 10. So that's 4 valence electrons. Okay, so I draw the symbol in the center, Si, and then I draw 1, 2, 3, 4 Lewis symbols around that. Okay, and that's the Lewis dot symbol structure for silicon. I can do it for magnesium and for magnesium 2+. Let me change colors. So magnesium is right here. It's in group 2. So it's there only after once I get past 10 do I do the 2 minus this. So I have 2 valence electrons. And so I draw the symbol, and it doesn't, there's multiple answers for this one. I can have magnesium this way, I can have magnesium this way. All these could be correct answers. What you will notice is that they are not paired. That would be the last one that way. I could do it this way, or I could do it that way. So all of these are correct answers for that magnesium. Now, magnesium 2+. How do I get the 2+? Means gave away 2 electrons. So I only have 2. So this one is magnesium. Whenever I have an ion, I have to put a box around it and say the fact that it's an ion with the charge on the outside. So that's magnesium 2+. There's only one answer for that one. This is showing the electron transfer. This is the same one I had on the slide earlier. So this is the Lewis dot structure for sodium. This is the Lewis dot structure for chlorine. And I want to draw that arrow. So I'm going to require, so this is a required answer. I'm not requiring this, okay? If you look in the back of the book at the problems in the back of the book, however, it does have this also. So, and whoops, that was not good. So for me personally, and I'm not saying this is a general rule, for me, not required. I just want you, I want to know that you understand where the electrons go, not necessarily what's formed there. Okay? So in ionic bonding, 2 things happen. The electron is removed from the metal and placed on the nonmetal, and this is step 1. Okay, it always requires energy. So this always requires energy. Which means it's a positive energy. And then typically step 2 is emits / gives off energy. Or from chapter 6, this is a negative energy. And so then depending on which one's larger, step 1 or step 2, is whether this is going to be a net energy. So this is the net here. So this is the sum of step 1 and step 2. So depending on if step 1 is larger, then it would be a positive value. If step 2 is larger, which in this example, then this would be a negative value. All right, I'm going to stop here, and we will make another video with the rest of this section.